today's video we're going to be going over section 8.2. This section is an introduction to series. So the objectives of this section are 1. To define a series using partial sums, then to define the geometric series and talk about when it converges, diverges, to look at the harmonic series and do the same, and then to get us our first test. Most of our tests will be for convergence. This one's going to be for divergence, and we'll do an example using that test. So let's get into it. So first things first, what is a series? Well, to do that you have to start with a sequence. So we're going to start with a sequence like in 8.1. Our sequence is a sub n, and remember that's just written down here as a sub 1, a sub 2, a sub 3. Actually I should write it here, a sub 1, comma a sub 2, comma a sub 3, just a list of numbers. Okay, so then in 8.1, and we're still going to need this, so it's a good reminder, in 8.1 we said what is the limit of this sequence? Right? As n gets really large, where does the sequence go? And we said if this exists, then I converge. If the limit does not exist, I diverge. Okay, so we had a sequence, which was a list of numbers, that could converge or diverge based on this limit we set up. So, what's a series? Well, a series is when we take a sequence, and instead of just looking at each term as n gets really big, we add the terms together. So that's here. We add our terms together, right? Forever and ever. You just keep adding more terms, adding more terms, adding more terms. And what we're going to be interested in, just like up here for sequences, was we're going to be interested in, does that equal anything? Does that sum as we add on another and another and another term, does that approach anything? So the way that we write these series, which are just adding up terms of a sequence, is with this. So what is this? This is a way to write out this sum, the plus and the dot dot dot. This first piece here tells us, well, what are we adding? That's our sequence a sub n. Then this piece here tells us, where do I start? What's the value I start with? So I would plug 1 in first. Okay, then this symbol here tells me to just add in between, and this is where I end. So for us, when we're doing series, we're just going to go forever, go to infinity. But you could define these to be finite. You could go from 1 to 10 if you want. That would be perfectly fine. Okay, so then the next thing is, if we've already done this definition, we know where it starts, we know what we're going towards, you'll sometimes see this slightly lazier notation. And it just means the same thing. It's just if you've already done the work to write out the start and end points and you're talking about the same exact series, you'll sometimes see some of the information left off. Okay, so what do we have to hold on to? A series is the sum, this infinite sum of terms from a sequence. Okay, so we are interested in this idea of what is that sum equal to, if it is equal to anything. So to figure out how to do this, we have to actually go back to what we did with integration. So when I gave you this problem, integrate f of x from 1 to infinity, what we ended up deciding was that, well, we can't just add an infinite number of things, right? That idea doesn't make any sense to us. But I do know how to add finitely many things. So we had this idea. I can integrate instead the function from 1 to t, and then what I can do is I can just keep increasing this upper bound and see what happens to the value of my integral. Maybe it's increasing, maybe it's decreasing, but does it go towards something? That's what this limit is. So then what we decided was, okay, that's not too bad, I can do these. It just gives me an integral I have to do, and then I just take the limit after. So it was almost two separate problems, right? It was do an integral, and then it was do a limit. Okay, so then sometimes we had convergence. So what were the options from this? Well, if the limit existed, we called it convergent. If the limit did not exist, we called it divergent. Those were the two options. So let's think about this construction now. Well, for the series, I'm just adding up a bunch of terms of a sequence, right? It's just adding, adding, adding. Well, I can't just do that forever. I don't know how to calculate that or if it even makes sense. But what does make sense? What makes sense is, and I'm going to change up the notation just a little bit here. What does make sense is I can add up a finite number of these terms, maybe the first 10, the first 20, then the first 30, then the first 40, and so on. I can add those up, get a number, because I'm just adding numbers, and ask myself, what is that set of numbers doing? Is there a pattern there? Is it getting bigger or smaller? Is it approaching something? And that's, again, just do a limit. So I'm, again, just taking this harder problem with this infinity as a bound, and instead of dealing with that, I'm saying I can just deal with the finite case and then let the finite case grow and grow and grow and then see what happens. And what we're going to end up seeing is that there's two scenarios here. If the limit exists, we're going to call it convergent. And if the limit does not exist, we're going to call it divergent. And what you should see here is these things are mirroring each other pretty well with the conclusions, the setups, everything. So let's dig into this and do a couple calculations and see what's going to happen here with two examples. So let's go to the next page. So what I'm going to do is set up tables for these so we can kind of try to play around. So a sub n, and we're going to do the sum from I equals 1 to n of a sub I in this column. Okay. All right, so let's start with 1. Okay, a sub 1 would just be plug a 1 into here. That's 1 over 1. And I'm going to add from 1 to 1. Well, that's just one thing, so that's pretty easy. That's just 1. Okay, next one. Let's go to 2. Okay, well, 2 now, I plug in 2 into here, and I get 1/2. And now I'm looking at the sum from 1 to 2. So I'll even write this one out. I equals 1 to 2. Okay, well, that's just a1 plus a2. And if I look in my table in my second column, that's just 1 plus 1/2, which is 3/2. What you should see, though, is I can actually just build from the previous part, right? Because what I should see here is that this second step is really just the first step plus my new point here that I'm adding in. Oh, don't use that color. So plus my next number. So let's see if that pattern continues. Okay, let's go to 3. Extend that. Let's go to 3. Now 3 would be my a sub 3 term is 1/3, and then my sum is going to be from 1 to 3, a sub I. Well, that's a1 plus a2 plus a3. Okay, but I already did a1 plus a2, right? That's 3/2. Plus now my new term, 1/3. Okay, so then we can play around with this, right? This is, I gotta get a 3 down here, so that would be 9 over 6 plus, and then I gotta get a 2 here, 2 over 6, so that's 11 over 6. Okay, let's do one more so we could see it again. So I go 4, that's 1/4. Okay, all right, so I go 1/4, and then that's the sum, I equals 1 to 4, and then of AI, which is then again just this piece plus a sub 4, which is 11 over 6 plus 1 over 4. Okay, so let's put that in the calculator so I don't mess it up on the video and have to make more edits. Alright, so that gives us 25 over 12. Okay, and then we just keep going. We keep plugging in bigger and bigger numbers in here and keep adding and adding and adding and see what happens. But what are we seeing what happens? What we're doing is we're taking this column here, this last column. Let me do that in purple. We're taking this last column and we are making something out of it. I want you to think about what we're making. I'm giving you here a value for n, and you're giving me in this column a number. So think back to 8.1. That's just a sequence. So we're defining out of this a new sequence, and that sequence that we're defining is called S sub n for sum, partial sum, right? In this case, this sequence would be 1, 3 halves, 11 sixths, 25 twelfths, and so on. And so our goal to know what's happening with this sum is to ask the question, what happens? Because this is just a sequence, so if I want to know if it converges or diverges, I just have to set the sum up. What does this do? Now, we have no proof of what's going to happen here. We have no tools right now for this, but I'm going to tell you already that this sum, this total sum that I started with here, diverges. Why? Well, because this sequence of these partial sums in here, they diverge. So how could we try to figure this out? Well, what we could do, and we're not going to go this way trying these problems out, but what you could do is you could take this sequence you have, 1, 3 halves, 11 over 6, 25 over 12, and if you could find a pattern for that, so I told you that this was this sequence. If you could find a pattern for this that involved n, so remember the n values were 1, 2, 3, 4. If you could find me a formula for this so that at any step all I'd have to know was n and I could tell you what the number is, then we could actually plug that into that limit and figure it out. So we're not going to go through and do that. We're going to develop tools that are easier for us to use to do these types of tests, but we could do that. Okay, so then let's do the b sub n example. So for b sub n, we've got n, b sub n, and then we're going to have the sum, b sub I, which is really, we're just going to call it s sub n. That's our new sequence we're making. So we're just making a new sequence out of this. Okay, so I put 1 here. All right, but that's 1 over 1 cubed, but that's just 1. Okay, next one is 2. That's 1 over 2 cubed, which is equal to, oh, I don't need an equal sign in there. That's equal to now 1 plus 1 over 8, because remember, it's the sum here, right? So I'm adding up all of the previous terms, which is equal to 9 over 8, okay? Now 3 would be, I plug in, and I would get 1 over 3 cubed, which is 1 over 27. So that's 1 plus 1 over 8 plus 1 over 27. But remember, we're just building off the previous term, right? So I know that this first piece is just 9/8 plus 1 over 27. And then the next one, this is 1 over 4 cubed. So this would be 1 plus 1 over 8 plus 1 over 27 plus 1 over 64. Okay, and then I would just keep going. And remember, I'm getting a new sequence out of each of these. Each time I go through now, I get a new piece of my sequence. So this is another piece, and now this is another one, right? So now my question would be, okay, here's n. So that's 1, 2, 3, 4. And I've got a new set of partial sums here, and that looks like this. Okay, so let's just do a couple quick calculations so we can kind of look at what these numbers are. 9/8 plus 1 over 27. That's 251 over 216. Okay, and then I'm going to add to that 1 over 64. And you could do these as decimals if it's easier for you to see what's happening. get these things. So let's actually just do that as a decimal. 1.125, 251 divided by 216 is 1.162, and then I'm doing a little rounding here, 2035 plus 1728, or divided by, whoops, that's equal to 1.178. So I see here that these definitely look different. This starts at 1 and I'm adding, but I'm not adding much each time. And it actually looks like the further I go, the slower this is getting, the smaller amount I'm adding here. Over on this side, though, for the 1 over n, the numbers are still pretty big. So that's 1, 3 halves. We're getting 1.5, 11 sixths, just as trying to figure out what this looks like, 1.83 bar, 25 over 12, that's 2.083 bar, and so on. So, you know, right over here in this 1 over n cubed, you might look at this and go, I'm never going to get close to 2. Who knows, right? We haven't shown that yet. But for this one here, it only took me 4 terms and I'm already over 2. So you might say to yourself, that's growing pretty quick. I wonder if I can get to any number. Can I just go out far enough and get to 10, to 100, to 1,000? And actually you can. That's why this diverges. I know it's a little weird to see, but you can get to any number by adding enough terms. In this example here, and again, I'm not showing you anything in terms of a proof, this one will converge. So that means this sequence here that we've created, this here, will converge as a sequence, which means then that this series will converge. So this is going to converge, this first one's going to diverge. Okay, so let's get these definitions down. So given a series that we have here, we let Sn, just like we saw, denote the nth partial sum. So remember, that's just, I'm going to add the first n terms. So nth partial sum means I'm going to add the first n terms. That's all this means. Okay? Now, when I do that, every time I do that, I get a new number. So you tell me an n, I give you a number. That's, again, a sequence. And we're going to denote that S sub n, that's a sequence, right? So we could give it that sequence notation. Okay, so this new sequence, if it's convergent, aka if the limit of that sequence exists and equals S, which is just what we call it instead of L, which we were doing in 8.1, if that exists, then we say that this series is convergent. Okay, so I start with a series. I make a new sequence out of that, S sub n, right? So I start here, I create a new sequence out of that, and then I ask myself, is this sequence convergent? And if the sequence is convergent, then the series is convergent, all right? And I call the sum of that S. Now, if that sequence is divergent, right? If that sequence, for whatever reason, goes to infinity, negative infinity, or just doesn't exist, doesn't even go to either of those, just doesn't exist, I call the series divergent. Okay. All right, so important series. So our first important series is a geometric series, and this geometric series has this form, a times r to the n minus 1. Okay, so this is a number, this is a number, this is our variable. So it's number times number to a variable. Okay, now a geometric series is really nice in that it has a property that if you just look and say, oh, this is geometric, I know what a and r are, then you know everything about this series in terms of what's going to happen to it if it converges or diverges. And the breakdown is, if this r, the absolute value of that is less than 1, then I'm going to converge. Just immediate, boom, If r is less than 1, absolute value, I'm convergent, done, and I even have a formula. I know that it converges to this number. Now, if the absolute value of r is bigger than or equal to 1, then the series will diverge. So in 8.1, we talked about this a little bit. This form should look familiar to you. So in 8.1, so the geometric sequence was a, ar, ar squared, and then you kept going. And we mentioned in that video that a was your initial value, whether it's a population or the amount of money you put in the bank, whatever. And then r, so that's a, and then r here is your growth factor, right? And so it's just like in biology or finance or whatever, wherever you've seen this type of exponential growth before, this is your growth factor. And you know from a class like that, if r is less than 1, that's decay. And if r is bigger than 1, that's growth. Right, so you've seen that before, so that's all we're saying here, is if you're in a decay situation, then the series will converge. And if you're in a growth situation, then your series will diverge. That's it. That's geometric. Right? So the only work for doing these geometric series will be to get the series you have in this form exactly, because it needs to be in this form exactly. No ifs, ands, or buts, no changes at all. It's got to be in this form. So let's try one out. So right away I look at this and say, it is not in the form that I want. It is not sum of a r to the n minus 1. First things first, there's no clear a, and a can be 1, so it's not written, and that's okay, but there's no clear a, there's no clear one number to a power. I've actually got two numbers here to a power, so somehow I've got to combine that into one. So what we're going to do is we're going to take it into two pieces. So the two pieces we're going to start with are 2 to the 2n, and we're going to use a bunch of rules here. So what are the rules I'm using? I'm using that a, some number, some constant a, to the power n, all to the power m, is equal to a n times m. That's one rule, exponent rule we have. What's another one? Well, I know that a to the n times a to the m is a to the n plus m. Okay, what else do I know? I know a to the n over a to the m is a to the n minus m. Right? So I've got a bunch of different rules here I can use. So first of all, I see that this is 2 then to the 2n, which is 4 to the n. Okay, so that's actually really close. That looks like a number to the n minus 1. I'm just off by that minus 1. So then what I need to do is figure out a way to turn that into 4 to the n minus 1. Okay, so I want to turn this into this. So my goal here is I've got to put something else right here so that when I combine it with 4 to the n minus 1, I'm going to get just 4 to the n. Now if you look at the rules here, the one that I'm trying to use is this one right here. All right? So I'm going to put a 4 here to the 1 power, and then what I want you to do is think, can you convince yourself that that's true? This side equals this side. And if you don't see it, just ask yourself, what happens when I multiply these two to the powers? Well, I add them. 1 plus n minus 1 is just n. So that works. All right, I'm in the right form. So we're going to go back to this, and wherever I saw 2 to the 2n, I'm going to make that 4 times 4 to the n minus 1. All right, let's deal with this 3 to the 1 minus n. Okay, so I have 1 minus n, not n minus 1. It's backwards almost, right? It's flipped from the way it should be. And if you think a little bit more about that, you should be able to convince yourself that that's the negative version of what I want. So if you're not sure about that, just multiply the negative back through and you'll see that you get the same thing. Okay, but then I know what happens here, right? I know that a negative exponent, I can get rid of that by moving what I have to the bottom. And there we go. I've got something to the n minus 1 power. So let's put that into our equation or into our series. Okay, so I've got things to the n minus 1 power, and then I've got a constant hanging out. So what I'm going to do is try to put things together. Okay, I've got my constant, and then I've got now those two pieces, and then I have another rule here that I have the same number. If I have numbers being raised to the same power in this form, I can rewrite them as 4 times 4 over 3 to the n minus 1. And there you go. I've got A, and I've got R. Geometric. Geometric. Okay, so I want to know what happens to this series. Well, let's go back. If I can get it as a geometric series, which I do, I look at the absolute value of my R. So let's do that. My R is 4/3. So then the absolute value of that is just 4/3, which is bigger than 1, which means my series is divergent. And there you go. That's it. So my series is divergent because the R that I found, the absolute value of it, was greater than 1. So my growth factor was 4/3, which means that I'm going to start at 4 and I'm going to grow, and I'm going to grow, and I'm going to grow at each step. And so I'm going to be adding bigger and bigger and bigger and bigger things. And so what you can think about that is then adding bigger and bigger and bigger things, well, then I'm going to go to infinity. That's the idea. Okay. So another important example you're going to want to remember is the harmonic series. So the harmonic series is this form. Pretty nice, simple looking one. All right, so we've actually played around with this already. So in 8.1, so section 8.1, we saw that the limit as n goes to infinity of 1 over n was equal to 0. Okay, so then the terms from this series, just the sequence I got from just looking at the terms here, they go to 0. They get smaller and smaller and smaller, not too bad. Okay, now we've got that in our pocket, so we'll hold on to that. The other thing from section 510 is that we have played around with this integral as well. And if you think back to what happened here when you did this integral, and this is good practice, you might want to just go back through this, it will be on the final. When I do this integral, I end up having it not exist. So this shoots off to infinity when I try to do the evaluation. This goes to infinity. So then this was a divergent integral. So my terms, my individual things I'm adding, they go to 0. But when I actually do the adding them all up, that goes to infinity. That is the same for this series. This series is divergent. Just like the integral was. The things I'm adding are getting smaller, but they don't get small fast enough. This is the same thing that happened to us with this integral case. They don't get small fast enough. Now, on the other hand, we just saw an example that I told you did get small fast enough. This one, n equals 1 to infinity, converged. So in the next section, we'll talk about the difference between these, but we've already kind of done that in that section 510, but we'll go back over that. So the harmonic series is 1 over n, and that diverges. So why is that so important? Well, once you know what a series does, you can use that to tell what other series will do, and we'll get into that later. All right. Okay, so the next thing, the last thing, is the test for divergence, and it starts by noting this theorem, which is very helpful for us. So if the series a sub n from 1 to infinity is convergent, so if the series is convergent, then it has to be that the limit of just the terms goes to 0. So if my sum actually exists, then the things that I'm adding have to get smaller and smaller and smaller all the way down to 0. That's what this says. So if the sum actually exists, then the terms that I'm adding have to get smaller as n goes to infinity. Smaller being getting closer to 0. Okay, so you might think, yeah, duh. Okay, whatever, that's fine. But we need this because this helps us get the test for divergence. All right. So first things first, the converse of this is not true. And when I say converse, I mean just take the two statements you have here. So here is a statement, here is one. Take these and flip them. What would that look like? It would look like if now the terms go to 0, right? If the terms go to 0, then the series converges. This is not true in general. Not true in general. We just saw the harmonic series where the terms got really small eventually, but it didn't matter because it wasn't fast enough and the entire series diverged. So just because the terms of the sequence are going to 0 does not mean it's going to converge. Now, it's useful if they are going to 0 in terms of what you should think about what's happening. You might say, oh, the terms go to 0, it might converge. And that's fine. You can try to use that and prove it converges. But that is not enough. You need extra. Okay, so why am I telling you this? Well, the idea here is if this is a true statement, which it is, and I get a convergent series, then the terms have to go to 0. That means for us to have a convergent series, the terms have to go to 0. So if I can show that this is not true, so if I can show for some series like this, if I can show for this that this is not true, if that does not work for my specific series, then that means my series is not convergent, aka divergent. This is called the test for divergence. If the limit of the terms of what you're adding together either does not exist or is not 0, you're done, divergent, that's it. So again, if I've got a series, right here, I've got some series, if I can just show that the terms here don't go to 0 as n gets really big, just the things I'm adding, I'm done. So let's see an example here. I've got this series, which you're looking at this and maybe going, I don't know what's happening. There's too many things going on. So I look at this and I say, okay, do the terms go to 0? What does that mean? It means just set up this limit and say, what does this limit equal? That's all I'm asking here. That's all we have to do is what happens with this limit. Okay, well, we got a couple ways of doing this. First things first, you could just try plugging in infinity. You can't see me doing quotes, but I'm doing quotes here. And you would get infinity over infinity, right? So from Calc 1, that reminds us of L'Hopital's. So L'Hopital's is on the table. It's definitely on the table. What else is on the table is this actually kind of looks rational, like a rational function. So then if we know anything about limits of rational functions, that's also on the table. But before we do any of these, we have to be thinking about this as a function like in Calc 1. So if I'm going to use L'Hopital's or this idea about rational functions, I need an actual function of x being a real number, not n only being a positive integer, 1, 2, 3. Because if I'm only plugging in positive integers, the idea of a derivative does not make any sense. So all I have to do is switch to x's to get myself into a function here that matches my original sequence, right? It matches for any n. If I plug n into either of these, that's the same thing. But now I've extended it to include other real numbers. Okay, so again, I still get infinity over infinity. Got it. Okay, so then step 1 of this, or attempt 1, or whatever you want to think of, is L'Hopital's. So then L'Hopital's says take the derivative of the top, which is 2x, divided by the derivative of the bottom, which is 10x. Okay, well, let's simplify. This is now the limit as x goes to infinity of 2 over 10, which is the limit of a constant, just the constant, 1/5. Okay, let's try the other way with the rational just to check ourselves. So remember, the limit of a rational function, so that's x squared over 5x squared plus 4. All we have to do is look at the highest power of the top and bottom, and we compare them. If we get the same number, then the limit is just the ratio of those two things. Cancel, cancel, 1 over 5. Check. Okay, so we got that the limit of the terms is 1/5. So what does that mean? We'll go back to your test for divergence. If the limit of the terms, that's this we just found, does not exist, well, we got 1/5, so it exists, so throw that out. Or if the limit is not 0, cha-ching, our limit was 1/5, that's not 0. So this is true for this example. Okay, so if this is true, we've got it, then the series diverges. So we checked this box, thus the series diverges. So by test for divergence, this series diverges. And there you go. You've shown that the condition of the theorem is true. This is a condition right here. And as soon as you've shown that the conditions of the theorem are true, you're good to go. So that's it. That's the test for divergence, which will be a really nice one for us. Okay, so then I'll be putting up another video going over these guessing answers. So it's really nice to be able to look at these and try to guess what's going to happen, try to use your intuition. Maybe your intuition's good, maybe it's bad. And then we'll go through and how to actually know what's going to happen with this. So, you know, I want you to try these out before actually looking at the answers. But it's helpful to kind of just try to get an idea of what's going on by just looking at the series. So I'll put that in another video. Thanks for watching, and I'll see you later.